Just 1 second. I'm adjusting.
Okay.
My just 1 second. It's Adobe is a bit slow.
Okay. Yes, we can see your screen now.
Now I'm trying to send it in full screen. Let's see if it still works.
Okay.
Can you see the
yes
page?
Yes, yeah,
Fantastic.
Okay.
Okay. Yeah.
Okay, I think we can start. Okay, so good morning, good afternoon to everyone. So I'm very happy to introduce you to Professor Carlos Ficcioni from the KTH, Royal Institute of Technology in Stockholm, Sweden. Just a few highlights about the extensive CV from Professor Ficcioni. So Professor Ficcioni is full professor at KTH on the Division of Network and System Engineering. He is also the director of the KTH Ericsson Data Science Microdegree Program, directed to Ericsson globally. He is also the chair of the IEEE Machine Learning for Communications Emerging Technology Initiative and founding general chair of the IEEE International Conference on Machine Learning for Communication and Networking. I guess that there was the first edition of this event was last April or May. I'm not sure. Right, Carlo? It was May 2000.
May.
Yeah.
May. Yeah.
May. Yeah. So. And finally, also, Professor Ficcioni is a distinguished lecturer of IEEE Communication Society. So Professor Ficcioni is going to provide us a lecture on communications for distributed computations. Carlo, many thanks for accepting our invitation to be part of this event. And the floor is yours, okay? Thank you again.
Thank you so much, Professor Cavalcanti, or I should maybe call just Charles, since we have been waiting for so many years. So
yeah, Charles is just fine. Yeah.
And it's really a great honor and pleasure to be here. And again, also based on this wonderful collaboration that we have had for many years, exchange of ideas and between Brazil and Sweden, and I'm very happy now to give this talk. This is somehow a new line of research that we are conducting, especially in my group, and essentially the idea that communications so far have been done to send information, but with the emergence of machine learning and artificial intelligence, communications will be done also to do computations in a surprisingly new manner. And this is
Carlos, sorry, we cannot hear you. I'm not sure if it's your microphone or something. Yeah. Pelo chat, né? Carlo? Carlo, can you hear us? Hello, Carlo. If you can hear us, we couldn't hear you since you started your first slide after the cover page. Okay, we are trying to reestablish the connection. Can you hear us, Carlo?
I can hear you.
Yes,
Yes.
I mean, sorry for that. But when you changed your slide for the second one, I mean, the first one with the description of the motivation model and so on, we lost your sound. So can we restart again? Yeah, we can't hear you yet. Yeah. Yeah. We are seeing you, but not hearing you, so at this moment. Não, eu acho que ele quando me tocou aqui, aí... Então...
Let's try now again.
Yes, let's try again.
Yes.
Yeah.
Yes.
We are hearing you quite well right now.
Okay. Let me try to share again.
Yeah.
And I hope it will work.
Yeah. Yes, I think we missed all your speech on the first slide as well. So I think you can.
Okay. Okay. In the interest of time, let me quickly go. And I suppose you can see the screen.
Yes. Okay.
Yes, that's right. Okay, so that's what I was let me try to be quick so we will catch up. and yes, machine learning and the wireless communications is a traditional separated research area, but in the last years there have been a lot of fruitful interaction. And yet there is many fundamental questions that we have to understand, because the data generation in general in wireless network is distributed, and we cannot have timely data collection and in general timely data analysis. We need methods that are suitable for this distributed nature. And another question is that traditional wireless communication systems are not intended to carry machine learning data. Because in machine learning, the individual data itself might not be that important. Instead, what is important is the analysis that is done out of the data. And in general, wireless protocols are not optimized for such tasks. There is many use cases where this is evident. For example, in smart cities monitoring, here with sensors on the intersections of these roads, and all the devices have to coordinate transmission of data to then coordinate the physical movement. data collections to monitor the environment, and so forth. And if we look now at the way traditional way machine learning is investigated, the strongest assumption is that data is available immediately in some central location, and then data analysis can be done. In a sense that from a telecommunication perspective, it is as if we were in the 60s, where data is servers and is immediately available to do data analysis. But data is set in 2020 decade, the decade of Internet of Things and artificial intelligence, where data is generated in a distributed manner, and we therefore need new machine learning methods that work for these many thousands or hundreds of thousands of devices per square kilometer that come. This is generating a set of very exciting research questions, which I have tried very roughly to share here. We have the set of questions, research questions, where machine learning to design, operate, and manage wireless networks. This is very useful when model-based methods cannot be used, for example, for high mobility communications, industrial communications subject to high interference. But again, traditionally, models of physical systems, these models have too much uncertainty, then it's best for statistical methods such as machine learning. A second set of questions is number one, because from my perspective, perhaps the most intriguing, is to fundamentally redesign communication systems so that they can be used to much better perform artificial intelligence services, any kind of artificial intelligence services, both the training, both data collection and integration, and as well inference, application of and execution of computations to get insights from data, to get predictions and so forth. And in the rest of this talk, I will be focusing on this for machine learning. Because again, this is perhaps one of the most recent interesting, exciting developments, and it's an area where essentially people are telling how we would to fundamentally redesign communication systems for artificial intelligence. And we are in a moment similar to other historical transitions where, for example, telegraph was introduced instead of sending letters, and or when the cellular phones were developed in the 1970s, 1980s, and people wondered, oh, should this cellular phone be used universally, or is just here a luxury for very few people? And many, of course, were skeptical about this. Do we really need fundamentally new communication protocols for artificial intelligence? Well, the answer is actually yes, I believe, because of the tremendous savings and efficiency that these new protocols would introduce. And I will give now a tangible explanation and motivation about this. And I will speak on the rest of this talk of analog over-the-air computation and the digital over-the-air computation. Over-the-air is one such new communication protocol that are already intended by design to perform computation such as those of machine learning. So far, it has been over-the-air computation analog, mostly analog, very recently, people have been investigating digital in the world in this direction. Let me start with the analog. And this illustrative picture will probably you the main message of what does it mean to have a communication protocol that performs computation. Suppose we have a
Sorry, Carlo. We missed your sound again. Can you try to reconnect? We are seeing your screen and you, but not hearing you. Carlo, hello. Carlo, I guess, I'm not sure if it's your microphone or something. Carlo?
Yes.
Okay. Sorry again.
Connected.
Yeah,
and
it sounds like, I mean, from time to time you are having a breaked sound. So we are not sure it's your microphone or something, but we missed, when you started discussing the slide number 6, we lost your sound again. Sorry about it.
Okay. Yes, it's certainly my fault. I'm traveling. I am at the moment not in my office. So
okay, yeah.
I guess. But let's try to work
yeah.
in this one.
Okay. Thank you.
And yes, thank you. On this slide here, I'm trying to illustrate the main concept of over-the-air computation, where there is capital K devices here that are transmitting information over this base station, and then toward eventually this server. And in machine learning, this data transmission does not need to be done on separated channel, FNTDMA or an STMA, but transmission can be done by any device at the same time and at the same frequency. The reason is that in artificial intelligence, we need computations on the data, not the individual data. And the simple example is the sum here. If these devices transmit at the same time and at the same frequency, then signals overlap and automatically a sum is performed at the receiver. We would have a tremendous advantage here in terms of delay, frequency usage, energy, and also privacy and security. Of course, the delay and the energy, because everyone is transmitting at the same time and on the same frequency. But also in terms of energy utilization, since now the device itself can transmit at much lower levels, and in the end, what matters is the sum here, the receiver, that has to be correctly computed, not the individual axis. So this entails great energy savings. And also there is a form of already of privacy and security, because everyone is transmitting at the same time. So in principle, it's more this. Is now this is the over, and it's the idealized stuff. So I will add some technical details and to this setup. And this is this very simple illustrative case where we have transmitters, suppose transmitters, and they are transmitting with analog modulation. And we're transmitting this cosinus carrier ST to
Carlo? Yeah, we missed, lost your sound again. So we are seeing quite well your image when it comes back. Yeah. Essas câmeras não gostei não, porque elas demonstram quanto eu estou ficando careca. Carlo? Oh.
Yes.
Hello, Carlo. Sorry. Carlo, from our perspective, it looks like it's your microphone. I mean, it seems that it loses the connection. Do you have, for example, the microphone of the laptop or PC, I don't know, direct one, not on the phone, for example?
I'm using now the AirPods. Do you hear me?
Yes, I think it's slightly better because it's the sound was breaking and then suddenly we lost everything.
Okay, let's.
It's quite better right now, actually. Yeah.
Ah, very good. Very good.
Sorry about it.
I'm sharing it now. The slides again. And
yeah.
Yes.
And the sound is really good right now.
Very good. Let's hope that it stays so. And with this slide, my point is that the transmission of two analog signals over the air naturally overlaps, using again analog modulations. And all this is in the assumption that the carrier of the transmitters is perfectly synchronized, and also that the starting point of these cosinuses are also perfectly synchronized in time, and which is in general not easy to achieve. But this is the standard assumption in the state of the art of over-the-air computation. Let's look at this state of over-the-art. And I will then show some of our research, our original research of over-the-air computation with analog communications. And after this, if I have time, I will also mention over-the-air computation, which is a very new research area.
This idea to perform computations by communication, it's relatively new, and it appeared that the first time, as far as I could dig, in 2005, in a research paper from University of California at Berkeley, where people were interested at doing additions of signals using sensor networks. And this was an information theory paper in the group of Gaspar and his PhD student Marcello. Then there's been quite a little time has passed, and some new ideas have appeared in 2009, where there was one of the first paper designing a practical analog modulations capable to do this computation of FDR. All this remained, in a sense, an academic curiosity until 2018, when then, for the first time, over there, computation has been applied to federated learning. And is perhaps is exactly the computation of federated learning that have then triggered an enormous interest in this domain, now testified by many papers that have been published since 2018. And until now, very recently, we have published a book where we have done a classification and an overview of this vast research activity of FDR computation using analog modulations. And we came up then with a classification of the research areas. And in this table, I report some of the key results of this now vast research. In this paper 3, for example, people have investigated how to do power control for performing computation with analog over FDR. In this set of papers 6 to 9, they have investigated how to perform over there computation and at the same time federated learning applying a gradient specification. In another area of research, people have been investigating not much the training phase, but rather the inference phase and how this can be done with over there. There have been activities also investigating the role of noisy gradients and how to do this scheme that so far was a star network in a completely distributed manner. This paper 13 is one of the first papers that introduces idea of peer-to-peer networks. And other methods have also, such as in this paper 14, have investigated the computations that appear in machine learning where second-order moments are used for training, not just first-order moment, but also second-order moments where we not only have the gradients, but also the Hessians and second derivatives. And in this paper 15, actually this is a book, Wireless for Machine Learning, we did a survey of this extensive literature of analog over FDR computation. Now, let me give, in this huge, quite research landscape, let me give you a new idea, which we have proposed from my group in KTH on over FDR computations and federated learning with analog modulations. So far, we have seen the concept of FDR computation with very ideal assumptions, such as, again, synchronization, perfect synchronization in carrier and in time, but also the receiver was noiseless. But in the reality, of course, in communication, if we transmit this signal W1.WK, and they go over the same channel, at the receiver, what we would get is likely something like this. It's the sum of what we are transmitting, but also every signal WK is attenuated of the channel HK. And at the receiver, there is also a noise that is acting. So it's, in general, this overall signal can be quite far from the simple sum of the WK, which we could be interested, for example, in federated learning. To make this sum now more similar to make this signal more similar to just the simple sum of K from 1 to capital K of WK, there is many ideas and techniques. One of these techniques is to apply an appropriate power control at the transmitters. And this is what has been proposed in this paper from the literature 16. In particular, in this paper, they have introduced the concept of a precoder term, BK, that the transmitter K uses before sending its signal WK. And also in this paper, they introduced the concept of post-processor, is this square root of eta, which you can see it as a multiplying factor of the received signal, and arranged in this manner because of notational analytical simplicity. And this multiplying factor, eta, that appears both here and in the noise, is there to trade off the accuracy in the sum with the amplitude of the noise. And in this paper, they have they've shown that there is an optimal way to choose the precoder, BK, and an optimal way to choose this eta, the post-processor. And they will have these expressions that depends on the number of devices, on the maximum transmit power, and on the individual channels. And in so doing, however, that is, if you apply these precoders, this post-processor, still we would have a signal y of t which is affected by estimation bias and in general an estimation noise, this is unavoidable because of these channels here and the additive white Gaussian noise at the receiver. So can we do more to improve the estimation of what we are interested in, the sum of just the sum of the WK, looking and using this YK? Can we have this YK here is an estimator of the sum of the WK because of the big K and the eta and the Z? Can we find a better estimator? Yes, there is various methods. One of the basic idea is to do static retransmissions. And this now I'm transiting to the next set of slides. And here I will be quick. But if you have been attentive so far, and you remember the expression of the received signal Y, now here we have a little, but just a slight complication. And the complication is that at the receiver, we are not just getting the signal once from the capital K devices, but we are also making a sum over capital M times slots. So we are transmitting more than once, we are retransmitting more than once the same signal, and then we are summing also the retransmissions. In so doing, it's possible to show, and this is our original result here, that we would get a better estimator of the sum of the WK, which is what we are interested to compute. And in particular, we have that under some typical assumptions that are used in the literature, some particular, if we take into consideration the basic federated learning algorithm, and we have convex loss functions, and we can prove that this way of doing the transmissions will do this upper bound on the estimation error. And here, just since I have a very limited time, fortunately, we cannot go into the many details, but here we will give an intuition of what's the performance gains we can get. On the y-axis, I have put the estimation error. That is how wrong is the computation that we are doing when we are using analog over-the-air compilation with retransmissions. On the y-axis, I have put the standard deviation of the additive noise at the receiver. And every line here is referred to a different number of retransmissions. And 1 is there is no retransmission, and 2 is 2 retransmissions, and 8 is 8 retransmissions. So we see that the estimation error significantly go down. So it's from this value here up to here significant improvement. And here on the right side, this is an illustration of the role of power control. The unaware means that one does power control as people have done in the state of the art in the literature. Aware means that one does a power control that is aware of the number of retransmissions. And it appears that if one is aware that there is a number of retransmissions happening and the power can be adjusted accordingly, then there is a significant estimation error improvement with the number of retransmissions. And here also I have again very quickly a test, an application of this of federated learning with the retransmissions. And this is just for you to give an idea of the classification accuracy, where we see that with just one transmission, which is what done at the state of the art, we have 60% accuracy in classification, and with the 8 retransmissions, the accuracy was significantly up, is around almost 90%. Okay, this was for retransmission with static channels, and we have a similar set of results for performing over-the-air computation with analog modulation and fast fading channels. But since I don't have much time, and so I connected several times and reconnected, let me jump over this part. And those who are interested, of course, you are very much welcome to ask me for these slides, or you can ask over the email for the detailed publications where we have presented these results. But now, in the interest of time, let me jump to our next section, and is the part of digital over-the-air computation. This new section here of the presentation is focused on the use of digital modulations, because so far all the extensive research results that we have also reviewed on the publication, on the book that I mentioned to you before, all those results are in the assumption that devices use analog modulation, and this is quite unrealistic in practice, since as we know, our devices nowadays, most of our devices are digital. And so here I'm introducing to you a fundamentally new idea, which we have called channel comp. It's a general method to perform computation of communication, and at the same time with the assumption that the modulations are digital. I will show you why this is a bit surprising result, and what is the issue with normal digital modulations. Let's consider just 2 transmitters, transmitter 1 and transmitter 2, and suppose that they are transmitting the analog value 3 and 9 respectively. But they are using at this time digital, this very simple digital modulation, BPSK. So this is different from the previous slides, where instead the modulation was analog. And suppose that we are representing 3 with 4 bits, which is this 4 bits. Suppose that we are representing 9 with these 4 bits. Then this is the signals that we transmit according to BPSK. 0, 0, 1, 1, 0 with this cosinus, 0 with the same cosinus. 1 is the inverse BPSK of the 0 cosinus, and the same with this other cosinus. The problem is that when we use a digital modulation, these cosinuses, they overlap with the R, and sometimes the overlapping is meaningless because it's actually just noise, like in this cosinus. And this cosinus, they cancel each other. And in this case, we get the cosinus, the two zero, they overlap constructively. That's good. But still, we would have uncertainty here. So in other words, if you use digital modulations as they are, and we don't do anything, then we get an incomprehensible signal at the receiver, out of which would be impossible to perform computations, as it was done with analog over-that computations. So what can we do to avoid this? Well, now we can do something very clever, and I will introduce soon what is the key element to circumvent this uncertainty with digital modulation and to perform computation with just the digital signals. It's a very fresh research area, as I mentioned to you before, and in this little table, we like tables, we do classifications. And in this little table, I have reported the very few papers that we can find around where people have been trying to use digital modulation to perform over the air. And most of the papers that are actually this set of papers that have assumed the digital modulations, they are very limited in the computations that they can do. And they are or they use very specific digital modulations. So we don't have yet complete method where we wish to compute whatever function we wish to compute any useful function of machine learning using whatever digital modulation. And that's what we have proposed. So let's go now to the original, the very original ideas from my group, and this is the idea of channel comp, a general computation method for communication and digital modulations. The idea is that we have a number of devices here, as usual, that they are transmitting values, and we wish to compute a function of those values here at the receiver. The signals here are supposed to be digital. Let's see how we can do this little trick. And let's see, in the interest of time, let me see if I can skip some of these slides. Let's start with the simple example. Let's go on with the simple example of the BPSK. And in the baseband representation of the signal, this is the meaning of the arrow. This is a baseband signal that are transmitted over the air. Suppose that we are computing this sum, the sum of x1 and x2, where x1 belongs to device 1 and x2 belongs to device 2. If we do now use digital modulation as a BPSK, and at the receiver, we give up the traditional way to detect BPSK signal. Instead, we redesign a receiver in a different manner. And we say that every time we get the receiver the value 0 here, which is the baseband representation for 0, and then this is associated to the sum 1. Okay? I will be slow. If you get to this point, you will have understood the key original idea. If I get the receiver at 0, it is always associated to the sum 1, because in BPSK the value 0 is the value 1 here, the analog value 1 in BPSK is transmitted with with this baseband signal, 1. So, for example, 1 plus 1 here plus 0 will be at the receiver sorry, the analog, yes, if I'm transmitting a 1 and the other device is transmitting at 0, at the receiver, I will get a destructive signal, which is 0. This is 0, and therefore I associate it to it the meaning 1. And the same idea can be applied for the other signals. This works also for the magnifications, but again, we have to define detection threshold of the signals at the receiver so that every time a signal is in these thresholds, in these regions, then we automatically associate it to the meaning of the computation. And this can be done also for QPSK and so on. And the general fundamental new idea is given by this picture. In this picture here, we have a domain F. This is the set of all the possible input value of the function F. And these squares here are the value x1, x2, and x capital K if we have capital K devices. They are expected into these vectors. And altogether are all the possible domain the values of the function F. The channel, the communication channel, will perform always a sum corrupted by noise and an additive channel. This means that any input here is mapped into some sum at the receiver. Now, the very key idea is that as long as this sum, corrupted sum at the receiver, is unique for whatever combination of the domain points of the function F, then we can uniquely associate a meaning. That is, we can uniquely associate a computation. And if the modulations and of all the devices for some point give a sum at the receiver which is not unique, then we can change the phase and the power of the binary or of the digital modulation so that the overlapping will be actually distinguishable. And therefore, we can associate a computation to the received message. All this is illustrated, now can be illustrated very formally mathematically with optimization methods. But historically, I found a very interesting parallel that of this idea, and this is the idea of the hydraulic telegraph of the 4th century BC, where at that time there was a war between Rome and the Phoenicians, and there was need of communicating quickly between Sicily and North Africa, the current, nowadays Tunisia. And to do this quick communication of messages, they invented, apparently Aeneas Tacticus invented this system. There was at the receiver, at the transmitter, there was a cylinder of water, and in this cylinder there was here a pole together with attached messages. Then the transmitter would start to let the water flow, go down, and the transmitter would stop the water flow when the level of the water arrived at the message that was to be transmitted. At that moment, the transmitter would signal with a torch of fire that he or she had stopped the water flow. At the receiver, there was a person that would do a similar thing. This person would start the flow of water when they got the torch signal, and would stop the water flow when the transmitter would signal with a fire that it was time to stop the water flow, so that the two flow would be the same at the transmitter and the receiver, and the complex signal in this way, even a long signal could be transmitted. So it was therefore just a matter to give a meaning to the water level. And this is exactly what is a bit more in a more complicated setup described by this picture. More formally, this is really formalized, posed as an optimization problem, where the point is to design a digital modulator here. This is the block of a digital modulator of transmitter 1, a digital modulator of transmitter capital K, and in such a way that the difference between the function that one wants to compute and the constellation point at the receiver mapped into a tabular computation, well, this error has to be minimized. Or in other words, we wish to find that the phases of the digital modulation and their amplitude, so that the overlapping of the signal will return at the receiver distinguishable values out of which we can deduce the computation that was to be done. And this is the overall transmission chain. This Q is the this analog value, X1 is analog value, Q is the quantizer. This is the encoder with the digital modulations. This is the channel transmission. This is the reception. This is the additive noise. This is the received value, and this is the tabular mapping. Now in a set of papers, we have explored how these optimization problems can be solved. And in general, these are very tough, quite tough optimizations. And PR optimization, one has to reduce, wants to try to find approximate solutions. And we have a set of now interesting results. I will be very, very quickly. One published in this paper 24, recently appeared on the transactions of communication, and that gives the necessary conditions for this digital scheme to work. And this is for any modulation. If then we use a very specific modulation, such as QAM, we are also capable to analytically characterize the maximum error that we can achieve with this computation scheme. And this is in another set of results published on this paper 25, which is provisionally accepted on the transactions on wireless communications. And then another set of results, this is channel comp 3, is the application of channel comp to blind federated learning. And here also we can show that federated learning works with this digital scheme, and we have guaranteed on the performance of the federated learning. This is also recently is provisionally accepted for publication on the transactions on wireless communications. Since I have 4 minutes left, let me give very quickly some numerical examples and insights, very quickly, really. And suppose that we apply our digital method, the channel comp, with 4 devices, 4 nodes. Suppose that we wish to compute the function f1 is the sum, function f2 is the product, the function f3 is the sum of the square, the function f4 is the maximum of the value. And we have an additive by quotient each channel, and we assume to also do power control as the result of our optimization method. In other words, we choose the phase and the power of the modulations appropriately according to the solution of our optimizations. And these are the results here, the very illustrative results. Here on the left, we have what would look the constellation points of the digital modulations for any kind of function that we want to compute. So this is the constellation points that we have to adopt for computing the max. This is the constellation point that we have to adopt if we wish to compute the product. And this is the constellation point for computing the sun. And here we have, on this right side of the picture, we have the normalized mean square error of the computation. And the set of figures with the circles refer to the sun, the computation of the sun. The set of figures with the triangle refers to the product. And OFDMA means doing communication in a traditional method with separated frequency and time channels. And instead, the channel comp is our method. And air comp is analog modulation. Channel comp is the digital, and air comp is the analog modulation. In general, it's possible to see significant performance, or very good performance of our digital method, and for most of the signal to noise range. And with this, I conclude. The conclusion is that in machine learning neural networks, we have very many exciting research problems. And one of the fundamentally new is how to redesign communication methods so that they help the execution of computation. And we have presented a digital method to do this, which is one of the first attempts to compute functions over multiple access channel with digital modulations. There is a lot of research to further develop. And with this, I conclude. And if you have questions, I would be very happy to answer.
Thank you, Carlo. Thank you for also managing the time. So I guess we have time for one question. We are running a bit late now. Anyone? I have one, Carlo. Regarding your results, so what about, let's say, different channel statistics? Can we insert them into the model in order to respect a different, let's say, power profile for the channel in order to keep the same performance that you have showed us?
Yes, that's a really good question. And this our method is based on an optimization that has to be performed. And of course, this optimization takes as input the channel. Let me go quickly there. Yes, this general optimization here takes as input the wireless channel, which is somehow will have to be estimated or has to be known in advance. Then a very fascinating question, as you say, is what if now the channel is changing, and what can we incorporate the dynamics of the channel? And yes, we are working on this. We don't have yet results to be presented, but it's actually possible to show that one can do this computation even with just a statistical knowledge of the channel and not just with the instantaneous knowledge.
Okay, thank you. Any further question? No? So, Carlo, would like to thank you very much for your nice presentation. So it's being transmitted through YouTube. Probably we are going to receive some comments and questions, and we are going to forward to you for our later interaction, okay? So again, thank you. Sorry about the issues with the internet and so on. And thanks for finding time in your agenda to present us that quite nice work, okay? Thank you very much. I would like to...
Thank you so much. Goodbye. Have a good continuation. Thank you.
Thank you. Marius, can you hear us?
Yes,
yes.
I can hear you. Can you hear me?
Hello. Sorry about the small delay. We were facing some issues with the previous presenter regarding microphone and internet issues. So, sorry. Very nice to see you, even in a small screen. So, we are about to. You have some time constraints as well. So we are moving forward. Now we are going to have. Can you share your screen, Marius? Can you?
Yeah. Let me.
Yep.
Yeah. So, can you see it in full screen? Yes.
We can see it, but not in full screen. Right now, yeah. It's just fine now.
I think it takes some time, yeah.
Yeah. Okay, so moving forward, we are going to have now the keynote speech from Marius Contores. Marius has a double, as far as I understood, enrollment with both Ericon in France and also the University of Granada in Spain. So in the sake of time, I'm just going to highlight Marius, some points on the CV. Marius is an IEEE fellow, has won a lot of, a very high number of prizes in conferences and best paper awards, and recently has won a very prestigious European grant on, European Research Council, ERC, grant on semantic communications, which is the main topic of his lecture right now. So Marius, the floor is yours.
Thank you, Charles, for the invitation and for the introduction. Do you see also the small screen with the camera? Should I minimize that, or you see only the slides?
We are seeing both, but it's up to you if you want. Okay.
Okay, maybe I could minimize that. So then I think it's better. Okay, yeah. So I'm going to present, I'm going to present the vision and some fundamentals, some recent results very briefly of this ERC, which is, it's indeed one of the most difficult research grants in Europe on goal-oriented semantic communication. I mean, it has been, I wrote it in 2019, I got it 2020, started 2021. There's still 2 years to go. It's like 5 years grant. So it's a long story, this work. But it's also one of the pillars that, revitalize this vision, this communication paradigm. And the objective of this talk is basically to persuade you that it's not just a hype or a fashionable thing. It's mostly something that we needed for specific cases. So, okay. So I'll start with a bit some generalities about the 6G because, everybody in communication and signal processing, they want to motivate it through some new generation that make us busier and busier. So we say, we have to solve these kind of problems. I'm not going to go to the different visions. There are like a lot of overview papers, tutorials, vision, some people taking, 5G, multiply everything by 100, 1000 and so on. So, but there is a bit of consensus on certain things. So definitely we are envisioning new services, kind of immersive, multisensory, AR, virtual reality, and so on. Some holographic communication and digital twins. These are applications that will have, will be beneficial for the industry as well, not only for the entertainment, the metaverse, or like operation from distance for the e-health and so on. So these are new services that I think the market and the people in the society needs them. And taking these services, then people say, okay, we need a new standard. We need a new kind of wireless communication infrastructure and technology. And now when it comes to these new technologies, different people propose different things, but there are a few concessions, I think, there if we check a bit all the papers. So AI will be there. We want it or not, we like it or not. So people are talking about AI native architectures, and standardization has started also putting AI under study. Now, whether this is going to be for the physical layer, whether it's going to be for the traffic, for the network orchestration, and so on, this is to be seen. But the thing are going for AI and for open architectures, Open RAN and so on. Definitely, we're going to have edge intelligence. We're going to have more and more devices at the edge where, traffic is generated, when the phenomenon is generated, and there are not anymore these basic sensors that just make measurements and send them to a central server or controller. They have some decision-making as well, capabilities and so on. And this will make an extra burden onto the wireless networks. we have the merging as well of, sensing, computing, learning is going to be distributed and together with the communication. And these make some interesting problems. So definitely now the problem is not only, let's say communication theory, information theory per se. We have to interact with what sensing is doing. Signal processing people will be very interested about, sensing or nonlinear signal processing you have to do. And also data are there. AI will be there, some feature extraction, some machine learning that we have to be used to empower certain capabilities. So the problem is becoming more and more complicated. Now, the question is like, do we need a new generation and why we need that? And if we take that, okay, 2G was for voice, 3G was without the visiophony and so on, and 5G people say, okay, it's mostly IoT. Then the big question we have to answer is like, okay, the 6G is going to be the wireless for what kind of systems, okay? Now, let's make a fast forward to 2030. And what we'll see is we have some emerging systems. I mean, they have been discussed for some time, but now we see it crystallize a bit. We're going to have all these cyber physical, mission critical systems. We're going to have some autonomous interactive systems. Think about, self-driving cars, all this platooning. And sometimes they don't have to rely on some base station, some central controller. We're going to have this swarm robotics, all these kind of smart IoT. So these kind of systems, they will need actually to have, of course, reliable communication as usual. This is more or less done, let's say, as a problem, but it has to be under real-time constraints. So real-time communication. They're going to have to do some timely and effective actuation. So they have to make decisions very fast, sometimes autonomously in a distributed manner. So we have to arrive to consensus in a timely manner. And of course, this decision making, especially when we have human in the loop, it should be explainable, trustworthy. So we cannot use any AI techniques. And of course, there's going to be a lot of computation all over the place. It's going to be decentralized, going to be on device, in network, and so on. So there's a lot of heterogeneous computation and processing. So, for example, this is the Arc de Triomphe from Paris, and this is very famous actually runabout where cars are converging and is one of the most difficult for some people. So just imagine that one day you want to do that. You want to do that with self-driving cars. So there's no driver, and these cars will have to exchange information so that collaboratively, on a timely manner, they will arrive to consensus to do some kind of collaborative maneuver so that they don't crash. So as you understand, we cannot go the old way of, okay, broadcast information, let the other process or broadcast information to the base station. The base station has like a lot of capabilities that will process everything and send information to the cars. Maybe we can do it for a couple of cars, 5, it won't scale. It won't go for like 50 cars because either you're going to violate the timing constraint or you're going to congest the network and so on. So can we solve that problem? And these are the type of problems that motivates this goal-oriented semantic communication. Because basically, we're going to have this hyper-connected intelligence. So we're going to have to generate, acquire, fuse, process, transport massive amounts of data, okay, coming also from different kind of sensors and devices. We're going to have to solve our optimization problems under challenging actually constraints, whether this is energy, which is becoming more and more critical now, computational constraints, has to take into account certain things about the AI capabilities like explainability, fairness, security is going to come back again. So what is going to happen is that then the network, the wireless network, will face the situation where they will have to deal, generate, fetch, handle in general, data that are high dimensional, so probably it's not going to be our famous Gaussian distribution, one round of variables, some multivariate, and so on. Maybe it's going to be high dimensional. Sometimes, distributions that we cannot even model. We cannot have an analytical model. We cannot even easily calculate the mutual information, let's say. It's going to come from different modalities. It's going to be multimodal and also distributed into the network. So different sensors will fetch different information and probably they won't be coordinated. So if we put the numbers down, this is like massive amount of data or strict constraints. And basically the big question is like, can we do that in an efficient manner that makes sense? Is it scalable? And then the question is that we do have the right theory and then the algorithms to implement. So let's see what we were doing in the past, or so far, let's say. So far, basically capitalize on Shannon's theory, the father of information theory, who started, who put the pillars and the foundations of information theory, which led to the communication theory, then the algorithms, and then the practice that we did. And basically, Shannon said the problem the problem there of communication was a problem of reliable transfer information. He took what we call the semantics, I'm going to talk about this, and the effectiveness out of the picture, and that was the right thing to do. That was like a master stroke to simplify the problem in a meaningful way so that he could solve and build a theory that, we found the optimal way of communicating, and it's something that is undebatably a super success story. And another thing as well that we have in his seminal paper is that the encoder and decoder are either jointly or centrally designed. So the typical thing, for example, a simple example, we have a common code book. We're not having situation where we have like multiple agents that they are autonomous, they can have even different kind of configurations. So that was there. So that theory led us to certain, practical things. But if we check how the networks have evolved, the generation are using this, what I call this maximalistic approach. So basically, every time we want to define a new generation, we kind of boost all the constraints. So we inflate the requirements. Now I want 10-fold or 100-fold data rate increase. Or the delay should go 1/10 of the previous generation, and so on. And then we end up having networks that, in order to operate, they need a lot of resources. We need over-provision. So, for example, I can do a surgery from, let's say, from France to Brazil. Of course, I can, put 3 fibers on the back, the core network, dimension everything, shut up everybody else and so on. Yes, of course, I can do it for 1 or 2 links. And I will have to do the provision. But the problem is that I cannot do it. It's not scalable, this approach. So the goal-oriented semantic communication comes to kind of revisit and augment this model, not to say it's not meaningful anymore, it's just to augment. And basically, let's check what, Shannon's communication model was the fundamental. There's an information source. So traffic is coming exogenously. Somebody's giving us traffic outside. Generation of data outside is not part of the system. Then basically from people doing physical layer, signal processing and so on, that's basically a pipe. So communication engineers think about, have a pipe and they don't care about what I transfer. For them, it's a sequence of random bits. I just have some metrics and I do my best algorithm for that. And normally, what I want to do is a kind of a reliable transfer information, but then I reconstruct the entire information flow, okay? And problems about causality and so on is left out of the picture. So goal-oriented semantic communication comes as I call a minimalistic approach. So the first thing is it starts from the data generation. So the main thing is that probably we have to care about what is the goal of the communication. If you want to see it as, task-oriented. So I have a certain task, okay? I don't communicate just for, there is an end for that, okay? So first of all, I need to know, why do I send these packets? Why do I send this information? To whom and how it's going to be used? Okay, that's, let's say, defined as a goal. So then, first of all, I will have to generate or acquire the traffic in a kind of an active manner, or in an event trigger way. So for example, you have a source, you're more from signal processing. So okay, you have a time series or something that represents, let's say, the detection of an invader in the university, let's say, okay? Whether this is a video, an image, or just like some pulse. Now, if nothing happens at night, probably this is gonna be flat, or it's gonna be dark, it's not the same picture. So what's the point doing some kind of periodic sampling in the way of like getting a snapshot of that and send it there to the other side, to the destination, just to say, okay, nothing happened. Okay, nothing happened, and so on. If we knew that what we care is, let's say, to find the invader or an invader that has these characteristics, then I can already start doing that at the source or where the phenomenon generated. Okay, so when I'm going to have an event, then I'm going to have to send a lot of information, do my signal processing as I have to do it, so then I can, represent that information into the other end. But then this means that I have to have the capability to generate the traffic at will, based on how the process evolved, how the time evolution of that it is. And of course, not all the things are useful or important for the application. So I can do some filtering. People from signal processing would be familiar with this censoring thing. Has been work in the sensor networks in the past. So this becomes relevant, but with a new kind of twist. And I have to go and evaluate which is the important data to send. And then I will have to reconstruct based on two kind of things, kind of a quantitative perception of the information, but also qualitative, because certain information may have the quality given the context that is sufficient enough to do my to satisfy my application requirements. Okay, so in a way, the destination now, in a way, what we do, we try to hardwire the application layer, where it's the end user, when it's the observer, when it's the decision maker that decides whether a certain piece of information was useful for his application or not. We have to bring all these kind of objectives and go all the way down to the physical MAC layer, take this into account, and inject it in all our signal processing and information theory. Okay? Now, the big question is that how do we do that? Because this is kind of a joint design. We can show that this is a non-separable approach. So it's a joint design, kind of unifying data generation, transmission, and reconstruction. There are cases where I don't have to do to reconstruct the whole signal. Okay, maybe I should do some kind of nonlinear signal processing where I get parts of the signal where I want it with high resolution, the rest is useless for me. And the way to go is like we need to define what we call the semantics of information, what has to do with the significance or the usefulness of information with respect to the goal I'm trying to serve. Okay, now the bigger problem that has this paradigm is basically what is the semantics of information? Apart from the fact that, after writing the ERC, and there's like certain people share the same vision with me, but then they start, going back to the recent definition from linguistics, and has become a kind of religious topic, whether it's semantics, pragmatics, effectiveness, and so on. But for me, it's like as long as we define it, we know what we're talking about. Okay? So, what is semantic information for us, let's say, is we comes from the etymological meaning of semantic, which comes from Greek, ancient Greek, actually, in even modern Greek, we use that, which is significant, which means important. So the semantics of information is the importance of the significant information. It's not the meaning of information, okay? But does not preclude that, but, there's a specific way we can discuss later if you want why I don't consider the meaning as interesting here. Now, to define it, we can define in different kind of resolutions, let's say. In a microscopic level, as I call it, it has to do with the realizations that I see in the source. Okay, I have a certain source, or I have a certain stochastic process, okay, that evolves, and certain, values or certain outcomes, certain events will have some relative importance. And the importance has to do only with the uncertainty or with the how likely it is or not. Because in the traditional way, if it's a low probability event, then it contains a lot of information. Now, what is the difference here is that I have two rare events, for example, very low probability. The one is just like, okay, doesn't have any effect on the system. For example, I'll tell you, oh, it's gonna snow now in the desert. You don't care probably. Okay, cool. Why not? But I'm telling you now, there is a fire the next building, which is very rare. But then you're gonna run out of the amphitheater. You see what I mean? So two different events that they have the same probability, low, and they have the same information content according to the entropy. You have relative importance depending on how we use them or depending on the effect that it has on the observer. Now, there's another way we can go. We can go to some kind of link level or kind of a small network. And this has to do with the innate and contextual attributes of information. We'll define a bit later. But then at the end of the day, this kind of a macroscopic view, kind of an end-to-end system, which I will detail a bit later. I'm going to speed up a bit because I think I'm getting a bit slow. So the first level, we can play with entropies, generalized entropies, and weighted entropy, so on, putting some kind of utility function or weight functions or value functions into the entropy. I'm not going to detail that. I'm going to detail something which has a bit more practical it's more easy to grasp. So to define the importance of information, we can have, let's say, this vector tuples of innate objective attributes of information. And this could be the freshness, how fresh is the information, the precision, the accuracy, and so on. And also we can have the contextual one. So I can have fresh information that arrives at the end, that arrives at the destination. Depending on the context, it could be a timely one or not. Maybe arrive earlier, can arrive later, it could be fine or so on. And this depends on the context of use, okay? The accuracy as well is something that has some kind of dualism. For example, a measurement has its own accuracy, and this is innate. It remains as it is. It will never change. I have 2, 3, 5 decimals. Now, the accuracy is also a contextual attribute because depending on what kind of application I have, this measurement is enough or not. If it's only 1 decimal, it could be fine for a simple application, but it's very, very critical. I don't know, the temperature of a nuclear plant. Maybe I don't know how many digits I might need to know in terms of accuracy. Okay? And on the top of that, there is something which depends on the goal, is the perceptual quality. How, let's say, the decision maker will receive that information and whether is able to make a decision based on that. Okay? And this is not necessarily something that is related to known metrics like, distortion, mean-square error, and so on. I have an example later. Okay? So we can say that basically the semantic information is this composite function when I have the vector of the attributes, innate and contextual, that we can have a certain relation between them, could be in general non-linear, and on top of that I have this context valuation, and I can include the cost. Give you a very, very simple example. I have two metrics. I have information freshness or age of information, as is known normally in the literature. So basically it's the difference between the time I receive the information and when it was generated, not when the transmitter starts sending. This is not a delay or latency kind of thing, because it changed completely the thing. I might have a very slow connection sending information that was sampled 1 minute ago and sent to me. And even if it's slow, it can be fresher. That's something that comes from an optical fiber very, very fast, but it has been sampled yesterday. So in terms of information, the freshness, the slow connection has more valuable information probably for some decision making, okay? And I get the accuracy could be like, the square distance between xt and xt hat. I have a certain stochastic process with xt, and then I estimate, just put the product of them, and then I have a timeliness function. So as long as the information arrives within that window, let's say my utility is constant, my timeliness is evaluated like this, but then it's exponentially decreasing. Okay, and based on this kind of information, this kind of metric, I can go and solve problems with Markov decision process problems, dynamical problems, when I can find the optimal policies when I have to generate information and transmit. Okay, now value information, age information, nonlinear age information, quality information has been proposed in the sense of a special case of this definition, basically. Okay, so I'll go fast here. So for example, we use these ideas on a problem where, for example, I have a discrete source, have realization, I say, okay, for me, rare events are more interesting, let's say. So the importance is based on is a function of the probability of occurrence, okay? So then based on that, I can give also some other meta values in the value, whether it's important or not. And then I want to have a specific goal. I have a certain metric, the semantic information, which is just a non-increasing function of the age of information. Here's kind of a timeliness metric. And I want to find how basically which packet I should send and what is the code length that I have to do it. So we can solve it with an optimization problem. And basically, given the definitions we gave for importance and so on, and some other techniques about filtering and, data censoring, here, for example, I can have the utility function in this plot. I hope you see the cursor. So I want to minimize that, okay? And then basically I could have 100 realizations, and then given the arrival rate of my realizations lambda, I have an optimal K star, a number of packets that I could send and, minimize my objective function. So basically you see that in where lambda 20, for example, when I have heavy kind of traffic, instead of sending 100 realizations when most of them is going to be useless, I can send less than 10 here and still optimize my utility function, okay? So I can, reduce significantly the amount of packets I have to process and send because they will end up being useless for the objective function I'm doing, okay? Just checking the time to see how it goes. Now, another thing that brings this semantic goal-oriented communication is that, the evaluation goes into the end user. So now who decides actually? Which is the one that says, okay, the traffic you sent me was good. It was enough. It was interesting. Is the observer, is the receiver, let's say, that they're collocated, okay? So what happened is that we need to know the goal of the destination, and sometimes we don't know it accurately. What happened is that this becomes kind of an interactive game. So suppose that I have a sensing agent, Alice, as usual, that see the measurement. So it sees, for example, it's tracking the trajectory of a robot, of a car. So she sees exactly how the car is going, and it can sample every time the trajectory and give you accurate information. So she has the data, okay? And then she wants to send information to Bob, that's the end user of the observer, who has a goal, G, okay? Now, whether Alice knows the goal or not, explicitly or accurately, it's a different story. Because what happened is that Alice has the data, and now instead of seeing the problem as like a push communication model where Alice is sending traffic to Bob on that direction and is pushing traffic, it's a problem which what we call pull-based model, where basically is the observer that does queries to Alice. So Alice has a certain knowledge about the goal. It could be accurate one, it could be a partial one. And it could even, Bob could train Alice onto that she has a better evaluation, a better estimation of the goal. And Bob is sending queries based on the data. Bob is saying, I'm gonna take a decision now. Now is what I want information. So it queries basically Alice about what is the status of your source, let's say. What's the status of the parameters I want to estimate and so on. So this kind of a Bayesian kind of problem, okay? When the problem becomes interesting and tricky when basically you have partial observability. As I said, Bob queries based on an estimation of the data of the evolution of the source, which means that I see only when I take decisions, but I don't know what happens on the other end, okay? Maybe the robot or the car has has accelerated in a way that I should have known it earlier to change my decision making, but I have only D hat. And then Alice is forwarding, sampling the source and say to Bob, oh, look, there is some evolution that you might be interested based on an estimation of the goal, okay? And of course, it can be refined with the posterior probability. So basically, Alice has a certain prior knowledge, so what can be measured with the entropy of G. And then, given the queries that we're doing and the information that the response that Alice sends, basically we can improve and send these semantic queries, which basically we try to have as high as possible the difference between HG and HG condition on the Y and X, okay? So basically we can use tools from information theory and play with this kind of interactive communication. It has also implications with games as well. Now, what is interesting here is also that normally Alice, we deviate from the case where we know a priori the distribution. Okay, this is the common assumption that we have in communication, but here we don't know. We sample. So we get data basically. Okay, we have, let's say, the empirical distribution. So what happened is that if we try and redefine the entropy as a way of a belief entropy, okay? So the agent has a certain kind of belief with set of distribution and a prior distribution, an assumption about the goal, okay? Then the Bayesian entropy can be defined as the entropy of X given finite number of data that basically will give the empirical estimation of D, okay? By this, we can define also the Bayesian mutual information. And playing with this kind of agent-specific Bayesian notion of the entropy, we have some interesting stuff where basically we don't have this data processing inequality, which means that data can add information and processing can help. Something that, for example, when we have this Markov chain information theory, we have this data processing inequality. And we can even show the information is not always beneficial, okay? This is a very general kind of Bayesian model. So all Bayesian approaches will be very, very relevant. Even from a learning point of view, Bayesian learning is going to be very, very relevant in this goal-oriented semantic communication. And what we have is that we did a very simple case of that. We're still building the big problem. Suppose we have an agent, okay, that collects data according to a certain process. And of course, it collects it based on the effectiveness that we'll have on a certain agent that does actuation and basically sends a knock-knock onto whether it has been served its goal or not. And of course, the agent is basically placing queries into the agent when it thinks that it will have to get information. Now, what we're trying to do here is basically you have the evolution of two processes on different ends. So from one side, you have, let's say, the sensing agent that sees the evolution of the source and could say, okay, now given your goal, there is something important that you need to know because it's the agent, the sensing agent that sees the evolution of the source. Okay. Now, from the other side, the decision maker has his own process on to when it needs information to decide. So think about the doctor that goes every hour on every patient to check what happens and what is the status based on measurements. Now, this will be fine because periodically is when the doctor needs to get the measurement. So you can plan this because the doctor is going to ask the query. Now, what happens if a patient has some abnormal kind of behavior or something which is kind of an emergency or an alarm, something that the decision maker that has his own schedule, his own planning of an hour, will not know and will have to trigger a decision there. So there is the one is the evolution and the importance of the source from one side, and the query is coming from the decision maker. And basically what we ideally want to find is a sweet point where basically they're perfectly aligned. The actuation agent asks information when the source is at its more interesting kind of samples. Okay, we modeled this as a constrained MDP problem, Markov decision process problem. There is a lot of modeling here. Of course, I'm not showing any kind of details, but I can send you we're just submitting the journal of that, and it's an ICC paper where we see that basically by doing all this, taking into account the effectiveness, we can heavily reduce actually the rate of queries and information that travels over the network. Okay. Now I'm going to change a bit the angle, less kind of dynamic or MDP problems, and go to something which is more onto the information theory rate distortion theory, and this brings back the notion of this perceptual quality that I talk about. Okay. So when I have this goal agnosis, as I will call it, information transmission, then I have, let's say, a picture, X, coming from a set distribution P of X, which normally I will compress in the optimal way, send it, okay, here there's no noise, is the rate distortion problem. Send it, let me close this one, okay. Send it with a certain rate to a decoder that basically is gonna reconstruct X hat, which belongs to a certain distribution PX hat. So basically the rate distortion problem, it's a classical one. For those who are not familiar, I want to minimize the mutual information between X and X hat. So basically it's compress the source as much as possible, subject to a distortion constraint that I will have. So I want the distortion between x and x hat not to go beyond a certain epsilon, okay? And this is normally the rate distortion curve for certain distortion. For example, this delta function could be the mean square error. Now, I'm trying to get. So suppose that we have these two cases, okay? The above one and the below one. Now, if, for example, let's take the third picture where I have this building, or the fourth one when I have this bicycle. I think we agree all that is the upper set of pictures that perceptually will let us detect the bicycle and so on, as compared to the below one, which is a bit blurry. Now, interestingly, the upper ones are the high distortion pictures. So pictures with low MSE, mean square error. And the below ones is the ones with the lower distortion, with a good MSE. Now, in terms of perceptual quality, though, the upper ones is better than the below one. And that comes from past work in computer vision, actually. And, you know, there are many papers, I just cite one on 2018 where I got these pictures, where basically good human perceptual quality is not, there is a tension between the perceptual quality and the distortion, okay? So the distortion per se is not enough to just solve optimally this problem. Because what happened is that the problem what comes is that I might get sample by sample the pictures and send them in kind of a low distortion way. But when I reconstruct the distribution coming from the X hat, from the reconstructed pictures, I don't have any way to say how close is this PX hat with this PX, the original one. Okay. And this is what will give me the realistic kinds, what we call the perfect realism things. If they are exactly the same distributions, they have the perfect realism because I'm able to reconstruct actually the whole distribution. This is for those who work a bit with unsupervised learning and generative adversarial networks, GANs, or the deep fakes, when I generate pictures of human beings that they don't exist, but they look like, oh, these are, of course, like a person, is because I sample from a distribution that implicitly I learn. And that's because the underlying thing is I minimize the distance between basically these two PX and PX hat, okay? And on the top of that, in the semantic goal-oriented communication, you can think of that I don't even have full observability of my semantic source, whether because this is a complex one, whether I can see also a finite number of measurements and so on, which is a remote source coding problem or a remote rate distortion problem, okay? Now, how do we take into account this perceptual quality? How do we make that I can control and have an encoder and decoder that gives me the below pictures? It's not only for pictures, of course, it's a general one. But the pictures are more good as an example. So I can add constraints. Okay, this is the second constraint I can add when I have the remote problem. Forget it for the interest of time. And then I have another constraint, which is a divergence between PX and PX hat, the two distributions, the one that the original one and the reconstructed one. And I can add this constraint to basically compress not only for, you know, low distortion pictures, but also pictures that when I will reconstruct the distribution will not be that far from the original one. Okay. And in terms of divergence, you can put Wasserstein, F divergences, alpha divergence, so on. Now, what you put there, it has to have certain properties for the convexities and so on. Is not either computational or analytical is not the easiest problem. It's not a trivial extension of rate distortion. And this comes under the name rate distortion perception theory kind of thing. So you see this red one, dark red basically, is the standard rate distortion when the sigma, which is the constraint on the divergence, goes to infinity. And then if I have to put extra constraints about the semantic quality, I get the yellow or the green and so on. Whether I have a coding scheme that I achieve that and so on is a different discussion, okay? It changes also the way we have to do coding theorems, okay? We have extensively worked on that. We have many results about F divergences, Wasserstein as well. and so on. We have also computational generalizations of Blachur-Alimoto, and it's a very interesting optimization problem for people who want the like optimization. It's a non-trivial problem. And recently we did it with some other divergence coming from information geometry, and it has been widely used in the machine learning community, the alpha divergence. So basically what we want to do here, we have the rate distortion perception function. So I want to have the infimum of the mutual information, and I have two constraints, the one on the distortion, okay, on the block, and one divergence between px and px hat. And I assume that x and x hat are jointly Gaussian, okay? So I'll do it for the Gaussian sources for analytical simplicity, okay? Then I want to minimize this subject to a mean square error, and the divergence is the alpha divergence of, not the Rényi one, we have to be careful here, the one of Amari, okay? Now, of course, solving the Gaussian rate distortion perception problem, the rate distortion perception function of the Gaussian is an upper bound of the original one, okay? And the alpha divergence has this expression. It's a bit tricky in the literature because it has two definitions from Amari, but you know, we can trace back that the first who proposed that is Chernoff, actually, in 1952. And this is the divergence, basically. Sorry, the alpha divergence between two distribution P and Q. Now, we derive this for Gaussians. So you do some maths, and then you end up having this expression for the divergence between two Gaussian distributions with mu sigma square and nu and rho square, okay? So then what we have to solve, basically find the optimal solution of this optimization problem. And it turns out that the parametric jointly Gaussian RDP solution, it has of this form. So the rate distortion function is the max of, this is a classical one, when basically I have the diversion constraint active. Whether I don't have it, comes into the solution of a polynomial, is the root of a polynomial with order alpha here. Okay, so basically I have to find the roots of this polynomial x alpha minus alpha cx, cr some constants and so on. Okay, so it's interesting also to find that the optimal solution comes from some polynomial equation, canonical form of that. Okay, here you see, for example, how is the root finding of the polynomial. For some cases I can find analytically as well. When the constraint on the divergence is 0.2. And these are basically the rate distortion curve for different alpha parameter of the divergence and constraint. Or you fix that and then you see the rate distortion, the rate versus the distortion, okay, for different alpha. We have the complete characterization of that. Interestingly as well, the alpha divergence is a special case of F divergence, but it's a very, very interesting from information geometric point of view. It has some specific properties, and it also has some good properties in terms of manifold, and it has connection with Bregman divergence. And it turns out that, you know, KL, reverse KL, and other known ones are special cases, including, for example, Hellinger and, you know, Pearson, that, for example, this result hasn't been into the literature so far. For alpha equals 2, the alpha divergence becomes a Pearson divergence, and we can get exactly the rate distortion perception thing. Okay, now I'm going towards the end. What I present is like certain pieces and certain models among other ones that we have. Now I will try to, you know, go into the high level and see what is the problem. Okay, the problem is that I have a semantic content, could be complex data, very rich data, and abstract that could lie on a topological space and so on. Then I don't know how to communicate that. I don't know how to process, how to sample all the time and reconstruct it here. So from a high dimensional space, probably I might need to do some kind of manifold matching, bring it to a low dimensional space, but I keep the key characteristic and the structural properties, exploiting the structural properties of this space. And then from here, I will have to do some feature selection, pre-process, encode in an optimal way, whether I have also, you know, noise or not. And I will have to reconstruct. And then basically, we should not forget that at the end of the day, it's not like a sample by sample reconstruction that I want. What I want is to recover the original source. So if I have this picture The problem is not just, take this picture, bring it into lower dimension, make it like, look like a Gaussian source that I know how to optimally communicate, get sample by sample, and you're done. Okay? It's a different story because at the end of the day, I don't care what I'm doing here. What I care is that somebody has, in a very, very efficient way, be able to reconstruct that kind of content, okay, up here. And this is kind of a generative model, and there's a lot of implication with generative models and generative AI. And what happened is that this is a communication problem that becomes less and less interesting, let's say. The communication, it just does not offer much interesting. But what is the interesting part is basically is an optimal transport problem. Because at the end of the day, I have semantic content with a certain distribution, P of X, and I have to transport it on the other side and get P hat of X actually, which is as close as possible. See it as, I give you a very simple example, a very simple analogy. So suppose that you have a book and you want to give the summary of the book to somebody. You want to send you read the book, you are the source, you read the book and you want to send the summary, okay? Or even more, if you have a specific kind of a goal, read the book to find the person who killed somebody. But let's say you get to go on the summary. Those are the traditional way, if we don't follow this goal-oriented semantic communication paradigm, will go as, okay, let's take chapter by chapter. I'll do the optimal compression. I'll do a summary of every chapter. I send every chapter on the other side. The other person puts all the chapter things, and by reading the summary, it will get the idea, okay? By sample, this is kind of the sample by sample or like block by block kind of compression. Now, suppose that you want to reveal certain, properties of the book or certain characteristics, and you know that. Then what you do is you read the book and you write the summary as you know that for the other person was going to be enough to get that. And by pre-processing that and sending, you don't have to, send, sample by sample, chapter by chapter. You just send the source in a way that in the reconstruction will be as close as possible to the original kind of thing. And so there is a lot of interesting problems and connections with optimal transport and so on. Now, what I want to say is that we are scratching the surface because, there are some people that are very, very optimistic that, it's going to be on 6G and, we have solved everything and so on. If you want something, there is like two big problems. The big problem here is that it's application-based or end-user requirements, and it's the decision maker that says that whether information serves the goals or not. So it has subjectivity. And subjectivity is very, very tricky to model mathematically. So it's not an objective kind of probability. It has a subjectivity, and then there are tools that have been in the past from fuzzy systems, entropies, and so on. But it's a tricky concept to formalize, actually. And what happens is that whether we're going to end up with having universal metrics, that's one of the biggest problems. So if we don't manage to, solidify that, then it's going to be a case-by-case thing. And of course, we have to think that, okay, we see a bit the small picture. We see just a link now. What I present is mostly a link. When we're going to put on a system, how do you know the goal? How the goal is, broadcasted to different sensors that is, in the middle of nowhere in the network. How sensors, which is collect and they are smart enough, but how do they know what kind of goal they serve in the network? So it's very, very tricky. And in certain case, we need to challenge or redefine the OSI layer even if we want to be efficient. Otherwise, probably most of these games are going to be lost somewhere here. Now, I'm going to skip that. I'm going to go very fast in the interest of time to a last slide. I go back to this end-to-end kind of definition of semantic. And I think this is the most interesting part, actually. It's just like the most tricky to advance. Or grasp sometimes. So at the end of the day, what is the fundamental problem that we're trying to solve here? I have an event, I have a phenomenon that is generated at a given time t1 on a given space in time, okay? In a given space point, x1, y1, z1. At the end of the day, I want to reconstruct it at a different point in space at time t2. So I have xt1 coming from a process, It's an event, the realization of a certain source. And I will have X hat T2, which gonna basically has to represent the state that the system observer one sees. So I want to reconstruct. So if this, for example, what the digital twin wants to do, or when I want to synchronize the two ends. Of course, you're gonna send information processes and so on. So you can compress it with the optimal rate you want. You're gonna have a minimum time duration. This is, you can take it as your bounds. Doesn't matter. You don't have to go to the details. It can be also here a bunch of networks here. You don't care. At the end of the day, what you want is basically to reconstruct and have at two ends the same kind of representation. You want the observer B has a timely representation of the state that the observer A sees. So you want that basically the difference between xt2 hat and xt1, even a function of that, goes to 0, and you want also to have them synchronized. You want to also have to do it in a timely manner. Now, what happened is that the evolution at the end of the observer A and time and importance and so on is measured according to what happens in the point A. And we have the point B, which also could evolve in a different way. Okay, and this makes that importance of information, relevance, and certain things becomes, information has some kind of relativistic way. It's a relative information. And also it's the evolution of the two systems, the timing aspects that will define whether information has been important or not, valuable or not. So we need to redefine, let's say, the kind, get inspired actually from relativity theory and use these reference frames and basically try to synchronize in a way the system in a kind of a macroscopic way. Okay, so here the idea is not to do relativity. It's just get the background, the analogies from the Thun paradox, for example, and do some kind of reference frame dependent system state evolution, where basically certain phenomena that we have in signal processing and communication is just some correction that would have the same way I have the Lorentz, transformations. Okay, and this bringing down, redefining the synchronicity, what means that two events are at the same time in a distributed system and so on, is what will bring actually a step ahead. Actually, not mention that here, you even sometimes have the base station in the middle, that you have a different kind of way. So if the base station sends you something and there's another base station sending here something else, you can have phenomenon where basically you can violate causality. You don't know which event has been in the distributed system has been first, actually. The notion of which event comes first in a distributed system is very, very tricky. So there's a lot of work to be done here. I won't go deeper. And actually, in the interest of time, I will skip the other slides. But what I'll have to say that, as I said here, we get inspired from relativistic kind of principles. It turns out that by reading relativity, we flip the problem and we solve an information theoretic problem for relativity theory. And it turns out that basically when we send information from, let's say, a spaceship to the Earth or something that doesn't move, and or the Earth to the spacecraft, there's some kind of inefficiency and imbalance between in terms of energy efficiency and transmission rate. This has been actually studied already in the 81 by Tom Cover and Jarrett, showing that basically the traveling kind of, the relativistic kind of traveling device, actually we need delta times more the energy, where delta is a factor that is related basically to the acceleration, to the velocity actually, and then the acceleration. So that has been shown that up to the specific trajectory, and we end up solving the problem. I don't go to the details. Solving the problem, this conjecture for basically any kind of trajectory, showing that it's always the case that basically the moving kind of, with relativistic speed, the moving device is always inefficient in terms of power, transmission, or rate. Okay? Has been published in the European Physics Letters. If you're interested, I can point you to the thing. So I think it's time to wrap up. So I presented let's say, few kind of foundational models and directions that we have to take so that we try to build the foundations of goal-oriented semantic communication, which is a new communication paradigm, actually a new paradigm of dealing with information, because it involves also processing, computation, and so on, that redefines two things: the importance of information and the timing aspects in a communication system. Now, this is a rich kind of research domain because there's a lot of fundamental things to be done, and we have to redefine and augment these prevailing, design paradigms we have. And as I said, if we want to tackle the subjectivity thing and the universality thing, I think one of the most promising directions is to put the timing aspect inside and, do the last part, as I mentioned, this mathematical theory of timing. I think is the key to, bypass these subjectivity issues that we have and put things actually in the common reference frame, let's say. Now, why this is interesting? Because we can show even with simple kind of cases, even without doing a lot of analysis. I like to do a lot of theory, but you can even do simple simulations. And with these kind of principles, you can show that you can have extremely interesting gains in terms of resource usage, energy consumption, computational efficiency. All you need to have scalable systems. So basically, if you want, this is the communication theory and signal processing that real-time autonomous system control systems will need if we want them to scale them. And control theory people are aware of this kind of interesting stuff, and they follow more than communication people. And also on the other side is like, depending what you like, whether you like more maths like optimal transport, learning, signal processing, there's a bunch of problems to solve here. Even for signal processing, there is even a goal-oriented inverse problems to solve. People that are more interested on signal processing, I can point you to other work that we have been done, more signal processing kind of things. It has to do a lot of nonlinear signal processing, super resolution, and so on. So that's, hopefully I persuade you that that's an interesting topic to work. For that, I acknowledge, of course, the support of European Research Council. That is a grant which is give us a lot of freedom to do things, which is what we call high risk, high reward. Thank you for your attendance. If you have questions, even now or later, if you want to point you on papers, literature, and things like that, feel free to contact me. Thank you very much.
Thank you, Marius. Thank you very much for the nice presentation. So we still have time for a couple of questions on your side? Okay.
Yeah, we can have some time, yes.
Some questions or comments here.
Hi, Marius. It's Marcello here. Thank you very much for, I'm looking for the screen with your picture. So thank you for your excellent presentation. I've seen a couple of presentations before that deal with semantic communications, and I was very pleased to go through your presentation because, well, first of all, it was sparkled with the Greek references, and I quite enjoyed that. But apart from that, I think that what set your, well, this will not be a question, it will be more of a comment and a praising comment, actually. And most of the presentations and webinars I watched and paper presentations that I watched on semantic communications put the transmitter on the goal-oriented dress, but actually it was goal agnostic and information-oriented, as you said. And I always looked at that as a very promising idea, but the explanations, in my opinion, so far, before I watched your presentation, always fell short of what I was expecting, because it was, in fact, goal agnostic and information-based, so that we only transmit when there's information, but and put all the responsibility of the semantic reconstruction on the receiver. And usually people just say, well, the context-aware reception will be left to machine learning. And this is arguably the most difficult part of machine learning and artificial intelligence, in my opinion. But I was very pleased to watch the way you put all this with the mathematical background and with the resources that we can look into and understand how transmitter and receiver can communicate and work in the semantic reconstruction and semantic-oriented communication. So thank you very much for this. Charles and I believe we're very happy to have chosen this presentation. So I'm very pleased with that. Thank you, Charles, as well. So this was almost like a speech. So I'll pass on the microphone to anyone who wants to make questions. And Professor Jutin.
So thank you for your talk. I am wondering how in your talk it was not so clear how what you said in this last slide, the promising gains, you take this into account. Because usually in performance, it is very nice, of course, if you have two solutions to try to include in the performance something which is the cost of the solution, and to choose probably, like the Occam Razor suggests, the simplest one, even if you have a very small gain in performance. If you have a complexity which is much higher, you have to choose probably the simplest one and to make this change. How do you intend or already did that in your works currently?
Yes, thank you for your question. Then if I take, for example, these MDP formulations, when we derive the optimal, sampling, data generation and transmission policy, the complexity is not that much, because actually sometimes you can even do a stationary randomized policy when you derive the probability to do that, and you go almost as close to the optimal. So if you compare with existing policies where they take into account age of information metrics, periodic sending of information, and so on, we don't increase much in terms of doing it, because what happens is we change the way we have the utility function, we model the problem, and certain tricks that we do how to define the importance. But the essence is not something which is like a completely, a heavy jointly optimization problem when I put everything together, and this is where the gains comes from. So just changing a bit the way of seeing and treating information. That's the key. And then the solutions are similarly equal, let's say, in terms of complexity. But the case, for example, we'll have a very simple example where what you care is you have a digital twin or a robotic arm. What you care, you want to minimize the real-time reconstruction error, not the average MSE, the real-time reconstruction error. So when I have a Markov state, basically a Markov source, and I have a state here, I want to have the state on the other side, and I don't have to have any errors. And if I have errors, there's a cost of that. And there's even a different cost whether I'm, in a two-state Markov chain, whether I'm like 0 to 1, I confuse, and 1 to 0. For example, you confuse a red light for green or a green for red, is not the same kind of cost in terms of the consequences. You change the things, you do the MDP, and basically you end up having that 95% of the packets that you get rid of was useless. So if I was just sampling on a periodic thing, you choose the period that you want, optimize it if you want. You do that, or you do based on the age of information. So I want to have always fresh information, but maybe it's useless as again because I don't have any change on the source, and so on. We show that you get 90% gains, and the complexity is not that much actually. It's just you change the way you tackle the optimization problems with these things. So that's also the idea. The idea is not to have, because I say it's a joint approach, not to just do a joint optimization problem. And God bless if you can solve it or not. It's exactly the opposite. Is by tackling things that this would try to find the fundamental things and the way of treating information, what is the important in that information. Once you reveal that and you pose the problem nicely, then you get the gains, which are significant, without having to do fancy stuff. Okay, not relying also on the machine learning, as we said. Okay, machine learning will play some role here, but there's still theory to be done. It's not an end-to-end machine learning problem. Just put a deep learning kind of thing and we'll do the things and the compression and so on and don't care about theory. This is not our vision. So if I reply your question, if I got it correctly, the cost and the complexity does not increase significantly, sometimes even simpler than something, or equally complex, but the gains are significant. I can point you to papers if you want.
Hi, Mario. It's Paulo. You talk after what you're saying at last by replying Professor Juten is that it looks like the idea is that as in compressive sensing where you're trying to compress data, okay, in your case is not your objective. Your objective is to find the right information that you lead to your let's say success in the communication or processing, whatever. Is that correct or not?
Yes, it's correct. But if you want to see it as a compressed sensing problem, for example, you could see it. I mean, you want to find the the minimum dictionary,
Yes,
right, to
yes.
build it. You can do it based only on what properties you have on your your source, but you don't know for what it's going to be used or how it's going to be used. Maybe you don't need all this information. So if I inject this goal thing onto the dictionary this construction, I can even have some kind of goal-oriented compressed sensing. Actually, there are some works on that. We have played with that a bit since you are mentioning. So it's an extra step. If you want to see it, there is compressive sensing there. If you want to see it only on a signal processing problem, there's an extra thing you can add on that and do things more efficiently.
It means that
even people on MIT, they have done this kind of goal-oriented inverse problems and so on. And you can find some interesting gains there. So I can point you to some literature.
Okay. I think you answered my question.
Okay.
So do we have another maybe final question?
Yes, a final one because I have to really go.
Hi, Professor Marcos. Just one little question is more related with a curiosity if you have to think about that to implement as a goal the fairness part of your when you are trying to reconstruct this information. For example, the example that you gave to make the resume of the abstract from a book. It could be that when you make this resume of a book, you have some implicit message or thoughts that another person can iterate takes. So have you thought about that, or is some work related with that?
So I have worked on fairness for kind of AI kind of thing and some methods with information theory, but I haven't, it's kind of for the moment a parallel work. So I only keep it as a fair AI kind of thing, and I haven't merged it with this goal-oriented semantic. But definitely, if you put it onto the picture, you can take this into account. But we're still far from merging the two things. We're still building the blocks to go there. But yeah, definitely, it's interesting. But I do parallel work on fairness on AI, but not jointly with this kind of goal-oriented semantic yet.
Okay, thank you. Would like to thank you again, Marius, for the presentation, for accepting our invitation. Sorry about, we are running a bit late for you.
No, we're fine.
Okay, so thank you very much, and we hope to see you soon in the conference.
Thank you.
Bye-bye.
Thank you very much. Thank you, bye.
Teremos coffee break, e antes do coffee break, só entra no coffee break quem assinar a lista de presença, por favor.
I'm adjusting.
Okay.
My just one second. It's Adobe is a bit slow.
Okay. Yes, we can see your screen now.
Now I'm trying to send it in full screen. Let's see if it still works.
Okay.
Can you see the
yes,
page?
yes, yeah.
Fantastic.
Okay.
Okay. Yes.
Okay. I think we can start. Okay. So good morning, good afternoon to everyone. So I'm